For you. Okay, shall we start? So this is the third lecture of algebra number theory. So today we're going to talk about something called ideal class group, and really talk about the failure of the unique factorization in this range of integers of OF. So let's briefly recall what we talked about last time. So F is a finite extension of Q, it's a number field, and we talked about how to define the range of integers inside of that, namely OF. And the last time we spent quite some time to talk about how a prime P factors in this bigger range. And let's say factors of P1, E1, PG. I'm going to give you some name for these exponents here. So let me be precise. For each Pi, we call corresponding EI the ramification index / degree. I don't know what. I think I've seen both. And inside of this, I want to say that if EI is bigger than 1, it's called a ramified. So say Pi is ramified. And of course, if EI is 1, that's Pi is unramified. Okay, so that's for each Pi. We can say each Pi is ramified or unramified, but just talking about the exponents here. And also, for each Pi, I have another invariant associated to that Pi. Just like over Z, you have, if you take Z mod the ideal generated by P, there you get a finite field of P elements. So in general, if you have a number field, you have a random integer, you can quotient out by this ideal Pi. And this will always give you a finite field. Because somehow it lives over the prime P, and you probably can guess it's going to have something to do with prime P. It's P to the Fi. It's going to be some finite field, which is a finite extension of Fp. The cardinality of that is is P to the Fi. So this Fi, this is called the I would call it inertia degree, and someone would disagree with me and call it residual field degree. I don't know. Really, it's understandable. Both concepts are understandable.
What is Fi here?
Oh, the exponent here. This is a number.
Yeah. What is it? How is it determined from Pi?
Oh yes, thank you for that. I'll say what is the how. You take the quotient, you count the cardinality of that.
Yeah.
And that's going to be a power for P. So what the exponent is that's the inertia degree.
Okay.
I will say in a minute that you have an effective way of compute that. Okay. So here's a big fact. Very useful. Which is that n should be equal to sum of product of these ramification degrees and the inertia degrees. So let's give it kind of a proof. But I want to enter the case where my range of integer is explicit. Namely, joining one element from the range of integer. So like when OF is equal to O, Z adjoint alpha. Or if P does not divide the difference of the two. This is precisely the theorem I stated last time. That in this case, I have an explicit way of computing the factorization of P in this extension field. Okay, so in this case, so say Hx is the monic irreducible polynomial, monic minimal polynomial of alpha. Then I know that by general theory, this is how the degree of hx is definitely n, the degree of the extension of f over q. That's because alpha generate f over q. And remember that in this way, in this case, we know how to factor p. Namely, if the reduction of hx mod p factors as g x g in fp adjoint x. If the reduction of the minimum polynomial mod p factors as this, then basically the ideal p factors as p join h1 x e1 all the way to p hg x eg. So that was the theorem we talked about last time. That if you want to determine how p factors in this ring of integer of a number field, you basically factor the minimum polynomial mod p of the generator, and it consists your primes this way. So this will be your so this will be your p1, and this will be your pg. Okay, and with this, you can either. It's not that difficult to show that in fact, if you take OF modulo P modulo H, let me just take the first one. So that's how we want to compute what the residue field here looks like. But when you mod P, and remember this OF is just really nothing but just the arc. So I'm really looking at F essentially. Fpx modulo h1x bar. And now h1x is an irreducible polynomial mod p. So this is nothing but just fp of degree of hi, h1. So basically, the initial degree of p1 is just the degree of h1 bar. Maybe here's, and this is what we essentially it comes down to. Now you see that the big fact we want to prove here that n equals the sum of ei and fi. Really, let me just write it. So now this equality is basically just saying that the degree of h bar is equal to, which is I guess e1 times the degree of h1 bar x e cheap. Just basically when you factor polynomial, the degree adds up. So when you factor your polynomial hx into the product of polynomials, the degree of h bar x will be just the sum of the degrees of each of the factors here. And the degree of each of the factors here will precisely be the initial degree of each of the primes we have over here. And therefore you have the sum of n equals e1 f1 and all the way to e g f g. Just to give you a really quick example. If my f is q adjoint root of d, there are three possibilities. For ramification, we call it ramification. That's n equals 2. So when you have n equals 2 and you want to write a sum of ei, fi. So there are three possibilities. The first possibility is that this prime p turns out to be a prime square. So that's the case when you write 2, n equals 2, as e times f, where e is 2 and its f is just 1. I mean, the typical example is in Q join I, you have this ideal 2, which is y 1 plus I squared. Of course, you can also have this prime P to be continue to be a prime. So that's when you again just have one prime above that. But now F turns to be 2, and E is just 1. Again, I'm going to give this example in Q join I. So this is the case if P is common to 3 mod 4. So that's the case where there's initial degree is 2 and not ramified. Ramification degree is 1. And finally, you can have the prime P to factor as 2 distinct primes. So P1 not equal to P2. So in this case, you have 2 prime factors. You get E1, F1, E2, F2. These are all 1. So 2 equals 1 plus 1. So this is the case when P is, again, in Q join I, if P is congruent to 1 mod 4, that's what's happening. This prime P factors 2 distinct primes. So that's, I mean, of course, if you have a general, more complicated field, you can have, I mean, this is kind of a combinatorial question. How do you make n as sum of a bunch of numbers? To have pretty much all, I mean, there is a lot of possibilities you have to consider. What can happen in general? Okay. And any questions? Good. So now let's move on to the next topic. So-called ideal class groups. So these are kind of just recap of what we learned last time, and we want to also use this opportunity to introduce the meaning of ramification degree, initial degree. So those are important concepts later on when you study number theory in depth. But now let's get back a little bit. So let's recall our somehow goal, or our goal for when we try to prove Fermat's, or when Kumar tried to prove Fermat's theorem, is that he wanted to factor the equation like this. Right? But then, of course, he ran into a problem of z adjoint zeta p, as we see. In many cases, they may not be a PID. So problem is that z adjoint zeta p may not be a PID. So kind of the resolution we introduced last time was that we want to use the factorization of ideals instead of factorization of elements of the ring. But of course, at the end of the day, people still care about the equations. So people still want to understand when is such ring a principal ideal domain. So here's a fact. Remember that if a ring is a principal for OF. Of course, any ring is a PID, then it's automatically a unique factorization domain. But for a ring of integers, UFD turns out to be the same as a principal ideal domain. So, as far as Kumar is concerned, he wanted to show that, he wanted to really be in the case where this zeta p is a unique factorization domain, so that he can, one can somehow use the tricks that we explained on the first lecture to kind of try to attack this problem. So the question is, in general, the problem is, in general, these rings may not be PID or UFD. So we want to ask the question, how far is the or general OF from being a principal ideal domain? I think this is kind of a very natural question. Like, the goal for this lecture is to give a kind of quantitative thing to measure how far the ring of integers from being a principal ideal domain, and therefore how far is it from a unique factoring domain for factoring things into elements instead of ideals. So for this, we want to introduce something called ideal class. Called ideal class group. Some people write ideal class group of F. That's understandable. But I think technically it should be ideal class group of OF. I think usually people write it class CL OF, defined to be the following equivalent classes of ideals of OF. We have to explain what equivalent means. Where alpha, where I have two of non-zero ideals. Okay, I want to exclude zero. Zero is a bit different always. I want to say two ideals are equivalent. I and J are equivalent if you can find a number, two numbers, alpha and beta, in the ring of integers, not zero, such that alpha times I is equal to beta times J. So what is this? What does this say? Well, maybe I'll give you an example. So what would be a good example? Let's see. Sorry, I'm really blank right now. So maybe I'll do this. So maybe say in the adjoint root of -5. Okay? So I have two ideals. I have 2, 1 plus root of -5. I want to say that these two are sort of equivalent. I mean, don't look like each other anyways. Okay? So why is that? So this is because, let's see, I have to pick two numbers. So if I multiply this, like 3, 1 plus root of -5, with this 1 minus, with this one, so I will get 3 minus 3 times root of -5. Excuse me. Comma. I just basically multiply this number onto each of the generators. So multiply on the first one, I get 3 minus 3 -5. When I multiply on the second one, I get 6. Okay. So the other one, I'm going to multiply with a different number, 3. Okay? Then you see that these ideals are really the same. Think about it, because you have 6 here. I mean, you can replace this by, you can add a 6 times root of -5 to this one. Another color. You can add a 6 times root of -5 to this one. So this term will become this 3 plus root of -5. Or you can subtract that if you want to go from this to here. So they're really sort of the same idea after you multiply by two principal ideals. So that somehow gives establish a to say what two ideals are. So you ask. So in some sense, like if one of the ideals I were principal, you can show that the other ideal J were also principal. So now for non-principal ideals, they're sort of non-principal or like they're equally far from being principal. If somehow off by some multiplication by some principal ideals, they're sort of the same. So that's the concept I'm trying to convey here. Okay? So you can check that this is actually equivalence relation. Now, so I said this is an ideal class group. So I will explain it as a set. So all the equivalence classes of these ideals. Now, I want to say group structure. The class of the principal ideals I can take to be 1, or any other principal ideals. They definitely define the same class because you can multiply this one by alpha. That's going to be the same as the other one multiplied with 1. So they live in the same class. So this is the identity in the class group OS. And you can multiply two ideals, as we said before. Then, in the same way, you can multiply two ideal classes. If one ideal class is represented by I, the other ideal class is represented by J, their product will be the ideal class represented by Ij. So this is independent of the choice of the representative you choose. And to define the inverse, we use the following. So we just basically take any. Let me write A in I. Any element. You can check. Well, it's good. Since we didn't really develop things theoretically, but this will imply that A. Just like me, just give an example. For example, if an ideal 2, so 4 will be in here. So that means 2 would divide 4. So that means that 4 must be equal to 2 times something else. Okay? So the same philosophy works in the ring of integers. In the sense that if A is a non-zero element in ideal I, then this ideal I would divide the ideal generated by A, and therefore A will be equal to I times J for some J. So therefore, in the ideal class group, you would think that, that. Let me just write it like this. So, in fact, you're going to have this. If everything works out, of course, everything requires proof. I'm not proving anything. I'm just somehow manipulating it so that it looks reasonable, right? So now you have the ideal generated by A equals I times J, and then therefore the ideal class for the principal ideal A will be the same as ideal class of I times ideal class of J. And remember, the ideal class of any principal ideal is it's an identity in the class group. So therefore, the inverse of I is just for this J, whatever the J that makes it work. So the upshot. This is an abelian group. Because of ideal multiplication, they're commutative. Okay? And on make a theorem, which I won't be able to prove, it takes a lot of time to actually prove it. So for a number field, the ideal class group is always finite. This is not a trivial. Well, it will follow from what another statement I'm going to say later on. But really, this requires that things should be number field. Sorry. Okay. So before giving an example of how to actually compute the ideal class group, let me say why do we care about ideal class group? I mean, I guess for one thing, I kind of explained why this ideal class group measures how far OF is from being a principal ideal domain, right? I mean, somehow question, why do we care? Well, for one thing, that this measures how far is OF from being a PID. That's one thing. Maybe I'll give you another example. This is kind of an example of why. So Kumar proved that, of course, we don't know. Of course, if that, I kind of explained that if the ideal class group, maybe I should also say. So say here, so if the ideal class group is trivial, it's trivial. If and only if OF is a PID or slash. So if the ideal class group is trivial, then everything's good. So in this case, definitely we know how to prove the Fermat's theorem for that prime P. But what Kumar did is that actually, as long as P does not divide the order of the ideal class group for F equals to Q join theta P, then Fermat's theorem holds. So he really used this ideal class group, which somehow measures how far this ring of integer of Q join roots of P from being a PID, and really take advantage of this group structure to somehow show that the Fermat's theorem holds for that prime P. And he realized that the only thing one needs to use is that P does not divide the ideal class group, but not ideal class being trivial. That's a much more released condition. So in fact, Z adjoint theta P is a PID for only P less than 19 for all primes. Whereas this condition, the other condition, so P does not divide the ideal class group, happens for all primes less than or equal to 100, except three numbers: 37, 59, 67. Of course, it's unfortunate we don't know. So for those prime P where P does not divide the ideal class group, these are called regular primes. Well, in the sense of Kumar. But unfortunately, we don't know whether they're infinite many regular primes. I'm not sure whether we should expect there to be infinite many or finite many. But again, numerically, I guess for the first 20-something primes, we see a lot of regular primes. So I guess this allows Kumar to prove a lot of cases of Fermat's theorem. Not all of them, of course, but and this is a very great achievement. This is like hundreds of years back. Okay, so that's one. I hope these two are good reasons to consider these ideal class groups. Are there any questions? Good. So now, let me give you some something I guess similar to the other classroom. We can ask the following question: how large is in general, how far is OF from being PID? Well, here's the first theorem. Or Zigo says that for E square free, as E goes to infinity, the number of ideal class group of the imaginary quadratic fields roughly grows like root of D. So, in other words, if you think about it a little bit more, it's for imaginary quadratic field, it's very unlikely that ideal class group is 1. It's very unlikely you're going to get something which is a PID or unique factor domain. So in fact, this was conjectured by Gauss. It's Gauss conjecture, but proved by proved independently by Hegener, Baker, and Stock. That there are only 9 imaginary quadratic fields which are PID. In this case, well, I can list all of them. Negative D is equal to -1, -2, -3, -5. Excuse me, not negative 5. It can get really large. This is a very interesting example. The largest one I guess is 163. So on Wikipedia, you can search class number for imaginary quadratic fields, and it will not Wikipedia. I think Wolfram, like Google, and you can have a list of all the imaginary quadratic fields of class number 1, class number 2, and so on. Okay, and maybe also want to mention the other case. What about real quadratic field? So this is a conjecture of Cohen-Landstra. I think in the original paper they're assuming E to be congruent to 1 mod 4. Doesn't really matter. The conjecture is about. What was the number? Oh shoot! I should prepare this. So something like this. These 4 digits might not be correct. About that many Q adjoint P's. Like, maybe you're safe. Q adjoint has, let me say, class number 1. I.e., the range of integers, in this case, is a PID. This is somehow a drastic contrast. For imaginary quadratic field, it's really difficult to get anything that's a principal ideal domain. Conjecturally, for real quadratic field, on the other hand, there are, I guess, a little bit over 3/4 of them should be PID, except you don't know which one. Statistically, as D goes to infinity. Unfortunately, not even known if there are infinite many. I think according to P, not even known there's an infinite many number of fields. Right.
Well, there's no other infinitely number fields.
Huh?
There's no other infinitely number fields.
You told me they're not. We don't know whether they're infinite number.
Sure. You didn't complete your sentence. You said it's not known if they're infinitely number fields.
What's number one?
Oh, yes.
Of course. Okay. Okay. Good. Yeah, there are infinite number fields. Okay. So yeah, if you assign graduate student a problem about one number field, you can have infinite many graduate students. That's the first thing we need to make sure. Okay. So there, I guess. So I hope you give you some sense of the number of this class group, ideal class group. Okay. So how to compute? In practice. So I want to use a theorem. Oh, let me sort of recall something. This will take up some time. So recall that the degree of f over q is n, and this f has usually the number I write down, like this is a typical way of writing. So there are R1 real embeddings and R2 pairs of complex embeddings. Recall that the complex embedding comes in pairs because you can when you embed, you can further compose with complex conjugation. So in particular, this tells you that n equals n R1 plus 2R2. Okay? And with these embeddings, I can define the discriminant of OF to be the determinant of this thing. Where F1 through Rn is the basis of OF. Okay? So these are somehow the invariants we learned earlier on. There's going to be a formula involving all these numbers. So this is a theorem of Minkowski. You show that every element in the ideal class group. Remember, each element in the ideal class group is an equivalent classes. It's an equivalent class of ideals. So there are a bunch of ideals there. So, but you can always pick one ideal I. So every element in the ideal class group contains one ideal I, such that the norm of I. For now, I'm just going to define that to be the number of OF modulo I. I'll give you more information later on. This is less than equal to a number, which is the discriminant, absolute value of discriminant of OF. This is a number you don't have to memorize, of course. Very few people can memorize that. Not done yet. Okay. It's absolute value because discriminant may not be positive. Maybe after you have taught algebra number theory for like 3-4 times, you can memorize it. Not for me now. Okay. This is called Minkowski bound. For number fields of low degree, this turned out to be a pretty good bound. Okay? So I want to say a little bit more about this norm. So first of all, the norm of an ideal is multiplicative. Secondly, the norm of a principal ideal is basically just the norm of the generator. When you take normal generator down to Q, you just get an integer. So you just absolute value of that integer. And also I want to say the norm of an ideal is 1, even only if the ideal I is just generated by 1, namely the whole ideal, the whole ring of integers. Okay. So for the remaining time, maybe I'll do one example. Think about to actually use this theorem to compute the ideal class group of a field. So maybe I'll do. I don't have enough time. Maybe I'll just do this one. Oh. Let me do this. My F and OF is Z adjoint, which is negative 14. Okay? So this is different from what I wrote down. I'm going to update my notes anyway. So the first thing to compute is compute. First step, compute Minkowski bound. So what is the discriminant of OF? Well, this is D conjugates 2 and 3. We're given I think we'll give an exercise or something as a fact that the discriminant is basically whatever is in the square root times 4. So that's 56. And what else do I need? So n is 2. So n is 2. So I have a one pair of complex embedding. So R2 is 1. So that's all I need to do. And now I need to compute the bound. So that's square root of 56 times 4 over pi to the first power, 2 factorial, 2 squared. Okay? So use Google or whatever. Use your calculator. No idea how do you do this? I didn't prepare this, but I prepared. Oh, this is 50. Shoot. Alright, equals to square root. Yeah, I should prepare this. 4 divided by 3.0. 4 divided by 2. So it tells me that I just computed. Okay. So what I know is that although this looks complicated, I definitely only need to look at ideals with norm less than or equal to 4. So if you want to look at ideals with less than or equal to 4, basically, they only need to factor 1. Oh, there's nothing to factor about 1, and 2 and 3. 4, of course. 4 is 2 squared. So basically, every element in the ideal class group will be represented by some factor appearing when you factor 2 and 3, and also 1. So let's see. So for 2, so remember, let's recall that. So step 2. So this is my OF. Okay. So the minimum polynomial for square root of negative 14 is x squared plus 14 to not like 0. That's the minimum polynomial. Okay, if I want to factor 2, what I want to do is I want to see, so I want to factor this mod 2, so this is just x squared mod 2. So therefore, my ideal 2 is just 2 comma root of negative 14 squared. However, I factor my multi-minute polynomial mod 2. It's going to give me how to factor my primes. Do the same thing for 3. So that's x squared minus 1 mod. I don't know, just keep going. Keep going. Mod 3, x squared plus 14 is just x squared minus 1. So you get x plus 1 and x minus 1. Now I know that 3 is equal to 3 comma root of negative 14 plus 1 and root of negative 14 minus 1. So a priori, this ideal class group is represented by the principal ideal always 1, 2 comma square root of negative 14, and this vector, and this vector. Oops, sorry. It's possible that some of these factors are the same, but it's possible. That some of these are in the same ideal class. Of course, this is something I want to rule out, but at least somehow I have only basically 4 options. The minimum thing like the easiest thing, like obvious thing I can do is that the size of ideal class group is equal to 4. It's a Billian group. So what could it be? Trivial at z mod 2, z mod 3, z mod 4, or z mod 2 cross z mod 2. So basically that's all, I don't know how many possibilities, but that's all the possibilities. At this point, it's going to be very difficult to, in practice, it's going to be very difficult to actually compute what the ideal class group is. So it really depends on case by case. So the claim, no time, but in this case, the ideal class group turns out to be z mod 4z. Let me get as far as I can, and then we'll continue next time. So we have these options, right? So obviously somehow I guess we know ahead of time that the ideal. Let's just say I know for some reason that the ideal class group is z mod 4z for no reason, and now this is the identity element, right? And I guess what else can I see from here? Well, let's see. Let's note that 2 is this ideal square. Remember, this will represent the identity, and this will be the identity in the ideal class group. So this ideal 2 comma root of negative 14 would be a element of order 2. We're probably going to be like if the order is 4, then these 4 elements must be distinct. So you would probably want to show that this ideal is a genuine element in the ideal class, which is not the principal one, right? And it has order 2. So the strategy is the following. First step is to show that this is not a PID. And secondly, I want to show that So that's only giving me elements of order 2. But the whole group has has elements of order 4, right? Now we see we have a list. Each element in the ideal class group must be represented by one of the 4 ideals here. So this is a identity. So this is the element of order 2. So the other 2 must be the elements of order 4 in Z mod 4Z. So basically, I want to show that this one has order 4. And if whatever we're claiming is correct, basically I want to show that this square is equivalent to this. And if we somehow reverse the thinking, really, somehow, if we had shown that this square is this order 2 element in the ideal class group, then this element would have order 4. And that would show that the ideal class group is actually Z mod 4Z. So let me see. When these... So these 2 will imply that this one has order 4. Okay. I guess I'm out of time, so maybe I'll continue this calculation next time. And we'll do these 2 proofs. And then moving on to the next one. I'll stop here.